and share my screen. Okay, so everybody can see my screen.
Yes.
Hey, hello everyone. Welcome to the Paleoclimate Advances Webinar Series. I would like to briefly remind people our code of conduct and the format of the webinar. By joining this webinar, you agree to follow our code of conduct. During the webinar, please offer constructive feedback, consider new ideas, show appreciation, encourage innovation, acknowledge teamwork, and share the air. The webinar has 2 talks. Each has 20 minutes with additional 5 minutes for Q&A. In the end, hopefully we will have another 10 minutes also for general discussion. I will give a 2-minute reminder for each speaker just to keep us on time. And I'm not sure whether Shi Junsen is here today. He will help us moderate the Q&A. Hopefully he will join us later, if not right now. If you have questions for the speakers, please either type them in the chat or use the raise hand function. As always, we welcome speaker nomination. You can fill out the nomination form on our web page or contact anyone on the organizing committee. Okay, it's great pleasure for me to introduce today's 2 speakers, Drs. Gabriel Pontes and Pedro DiNezio. Dr. Gabriel Pontes is a postdoctoral researcher at the Climate Change Research Center at the University of New South Wales, and also at the Australian Centre for Excellency in Antarctic Science. He has expertise in large-scale climate and ocean dynamics. His research interests include polar warming, ENSO, thermal highland circulation, teleconnection, and feedback between high and low latitudes, as well as abrupt climate change. Dr. Pedro DiNezio is an associate professor at the University of Colorado Boulder. Pedro studies the influence of the Pacific Ocean on our climate's weather and climate. With a focus on ENSO, Pedro's research aims to predict natural and human-made changes in ocean and their global impact. Pedro has published extensively on climate change, contributed to IPCC, and is a member of NOAA's CPC's ENSO diagnostics panel. An environmental activist, Pedro works to protect beaches and coastal dunes in Argentina from erosion caused by sea level rise and unsustained urban development. Okay, it's great. Let's get started. I will stop my screen sharing, and I will let Gabriel take away. Let me stop my screen sharing. Okay, please take away.
Yes, I'm just sharing. Can you see my screen?
Yeah.
Okay, so hello everyone. First, I'd like to thank you, the organizing committee, for this invitation to present my work here, and thanks, Jung, for the introduction. And today I'll be talking about the impact of the background state on ENSO variability. And the idea here is to start to build a framework where we could try to try to explain how ENSO variability is affected by the different background climate states. So we have a variety of main features of climate change that we have seen in the past and we are going to face in the future. For example, we have changes in the ice sheets, then changes in orbital configuration, even in atmospheric CO2 that are known to affect ENSO variability. And we now have a quite of let's say a large ensemble of climate simulations from the Paleoclimate Model Intercomparison Project and from the coupled model intercomparison projects. It's both the PMIP4 and CMIP6, which are starting to showing us a quite consistent ENSO response under the different background states. And just a brief overview of the ENSO dynamics for those who are not familiar with. So ENSO occurs in the equatorial Pacific, and under normal conditions, what we have is the trade winds in the equatorial Pacific pushing surface waters west, pushing those warm surface water westwards, and these increased convections under the maritime continent, and creates a Walker circulation with a descending branch in the Eastern Pacific. And this is also influence some oceanic features, and the main ocean feature that's affected here is the thermocline. So we can see that the thermocline is lower in the Eastern Pacific and deeper in the Western Pacific. And when we have the weakening of those trade winds here, we have a series of processes that are triggered and displace those warm waters from the Western Pacific to the Eastern Pacific, and change all of the climate setting in the equatorial Pacific, with teleconnections from many regions across the globe. And as we can see here in this coupled system is very complex. And in the literature, we have seen a number of processes that have been suggested to be controlling ENSO variability. For example, those top two studies here, they say that the zonal SST gradient is an important factor in controlling the ENSO variability. We then have, for the early Pliocene and for the last glacial maximum, studies that have shown that the thermocline depth seems to be more important than the zonal SST gradient. We then have the intertropical convergence zone, which is going to be the focus of this presentation. Then we have, for future projections, ocean stratification as a key process in understanding how ENSO variability will increase in the future. For the past few decades, we have cross-equatorial winds, which are meridional winds in the equatorial Pacific, controlling not only ENSO change, but also ENSO diversity. And for many paleoclimate simulations and for paleoclimate periods, we have orbital configuration as one of the main forces that can control ENSO variability. And for the mid-Pliocene, we have also a study that shows that changes in the Sahara vegetation could also be linked to ENSO activity. So, as I told you in the beginning, we have now lots of simulations for key past warm climates that have been under intense investigation. And we have also the future projections. So this gave us a large ensemble to work with, and under those different background states. So at the right end of this figure, we have the future projections. Then we have this historical period. the pre-industrial at 1850, and before that we have some key paleoclimate periods, which are the mid-Holocene, the last interglacial, and the mid-Pliocene. So I will start to show you some results from the mid-Pliocene, and then we try to expand that towards the other paleoclimates and to future projections. So what the models tell us about the ENSO dynamics or about ENSO variability in the mid-Pliocene is that there is a pretty consistent weakening in the variability of the equatorial Pacific. So the top panel here, I'm showing you the change in the amplitude of the sea surface temperature variability, which is a measure of how variable the sea surface temperature was during the Pliocene. And we can see that the model show a significant weakening in the equatorial Pacific. And if we take here the red box, which is the Niño tree region, it's a key region for ENSO dynamics, we can see that there is a near unanimous ENSO weakening across the PLIOMIP models, which were the models that simulated the mid-Pliocene climate. And after looking at a variety of processes that could be affecting ENSO variability in those simulations, we found that the ITCZ was the main feature associated with this reduced ENSO variability in the PLIOMIP simulations. So on the right panel here, I'm showing you the change in the tropical precipitation. And those bluish colors show regions of increased precipitation, and we can see that there is a consistent increase in the precipitation over the tropical northern hemisphere, and a decreased precipitation in the tropical southern hemisphere. So this kind of dipole pattern indicates a northward movement of the ITCZ. So it's a northward shift of the ITCZ. And the scatter plot here on the left, where we have in the x-axis is just the change in the ENSO amplitude, and on the y-axis the change in the ITCZ position. So taking into account the tropical change in precipitation, and we can see that as the ITCZ moves northward, we have reduced ENSO variability, and this is very consistent among the PLIOMIP models. But how exactly does the ITCZ affect ENSO variability? So there are a number of processes that are affected by this northward movement of the ITCZ. So what we see in the mid-Pliocene is that the ITCZ, which is represented here by this blue band, moves towards the northern hemisphere, mainly because the polar amplified warming in the northern hemisphere was of a higher magnitude than the polar amplified in the southern hemisphere, and this results in a atmospheric energy imbalance. And the way that the climate system solves this imbalancing is by intensifying the southern hemisphere's Hadley circulation in order to export this excess of heat from the northern hemisphere towards the southern hemisphere. And so what we have in the southern hemisphere is an intensified Hadley circulation, and also intensified winds in the subtropical southern hemisphere. So this creates stable conditions in the tropical and southern hemisphere with very intense winds. And so the first process that is affected by this northward shift of the ITCZ is that it suppresses the equatorial convective feedback in the in the equatorial Pacific, because the further north, the further away the ITCZ is from the equator, it will suppress any anomaly that could enhance the convective feedback. In addition, those intensified winds in the southern hemisphere, they suppress the variability of the winds in the Western Pacific, which are known to initiate some ENSO events. So the weakening of those, and not only the weakening, but also the reversal of those winds, they are known to trigger the displacement of warm waters from the Western Pacific to the Eastern Pacific. We then have this process here, which is called as the Southern Hemisphere buster, which where anomalies propagated from the Southern Hemisphere towards the equatorial Pacific, and they also are initiating some ENSO events. And we then have the South Pacific meridional mode that also occurs in the South Pacific and propagate anomalies into the equatorial Pacific, starting in El Niño events. But those intensified climatological circulation in the equatorial Pacific suppress all of those events, and thus resulting in a weaker variability not only in the equatorial Pacific, but also in the South Pacific. And if we take into account only the models that better simulate this convective feedback in the equatorial Pacific, which is key for this mechanism, we can see that the northward shift of the ITCZ can basically fully explain the reduced ENSO variability in the PLIOMIP models. So we have looked at the mid-Pliocene, and we have seen that the model shows some very consistent mechanism for the mid-Pliocene. And a kind of a straightforward question is if it applies to all the climate periods or projections, or even future projections. So let's have a look at what happens for all the climate periods and for future projections. So here what I'm showing you is the sea surface temperature change in the equatorial Pacific, and also the changes in the winds. So here those figures were plotted in order to, so that would be easier for us to see regions that shows regions where we have SST, or how the SST gradient changes in the equatorial Pacific. So for example, here for the mid-Pliocene, which was the simulation that we were looking at, we have those intensified circulation in the southern hemisphere. So here with cooler SSTs than the tropical Pacific, and regions where with warmer SSTs than the main SST in the equatorial Pacific. So what we can see here is that for the mid-Holocene and for the last interglacial, those changes in the equatorial Pacific mean state or in the tropical Pacific mean state are very similar to the ones that we have shown for the mid-Pliocene. But those are completely different from what those same models are simulating for the future scenario. And here I'm taking just the high emission scenario, where we can see that there is an equatorial enhanced warming with reduced trade winds in the equatorial Pacific. And if we look at how those models simulate ENSO variability, and we are again here taking the Niño 3 region, we can see that For the paleoclimate periods, which are the mid-Pliocene, mid-Holocene, and the last interglacial, those models, they simulated they tend to simulate a reduced ENSO variability, similar to what we have seen for the mid-Pliocene. And if we take the mean state of the future scenario, what we can see is that there is a quite consistent increased ENSO variability associated with a different mean state. So this means that for ENSO dynamics, we likely have no past analog, because the mean state change in the tropical Pacific for those key past warm periods are different from the ones that we expect to face in the future. And then looking at those different mean states, we can go back to our main mechanism, which was associated with the intertropical convergence zone. And here what I'm showing you is how the tropical precipitation is projected to change in the future projections. So what we have here is a trend that indicates a movement of the ITCZ southwards towards the equator. But then we also have a movement of the South Pacific convergence zone towards the equator. And if we take a similar metric that we were using for the mid-Pliocene, where we just try to find a kind of a mass center of the precipitation in the equatorial Pacific, and then those changes would basically cancel out, because we have a movement of the ITCZ towards the equator, and a movement of the SPCZ towards the equator as well. So that's a southward movement of the ITCZ, but then we have a northward movement of the SPCZ. And when taking into account the tropical Pacific precipitation, we would have like no change in the equatorial Pacific. So what we did was we take the change in the ITCZ and in the SPCZ in the South Pacific convergence zone separately. And so what we can see here is then taking those two. So taking those changes separately, what we can see, what I will show you is just some results. What we can, and then we have to change a little bit how we were looking at the tropical Pacific and how ENSO responds to those precipitation regions. And what we did was and taking those two regions separately, instead of measuring the northward or the southward displacement of the ITCZ and the SPCZ, we would better show you on how on how those regions move poleward or equatorwards. So this results in this graph here when we take into account all of the paleo and the future simulations. So here we have basically most of the paleo simulations with a poleward movement of the ITCZ and the SPCZ, resulting in reduced ENSO variability, as we have seen. Then we have those red dots here, which are the future projections that tends to show an equatorward movement of the SPCZ and the ITCZ. And when we incorporate the abrupt for CO2 simulations, we can have this full relationship here, because then in the abrupt for CO2 simulations, we have some models showing the ITCZ very close to the equator. And then we can try to build a mechanism based on that. And we have seen that, for example, for the mid-Pliocene here, we have this kind of mean state, which is a very strong mean state, a very strong circulation that tends to suppress ENSO variability. And another kind of mean state that would tend to suppress ENSO variability would be a static mean state in the equatorial Pacific, where we would have a flat thermocline, reduced trade winds, and the ITCZ and the SPCZ located very close to the equator. And then we have another mean state that tends to enhance ENSO variability. So we would have this kind of bistable ENSO dynamics with two mean states that tend to reduce ENSO variability and one mean state that enhances ENSO variability. And this is important because about 10 to 15 years ago, we had some studies suggesting that ENSO could be a potential tipping element of the climate system, but then we just didn't know yet how ENSO would behave under those different climate states. And now we can try to move towards understanding this, how ENSO could be related to a bistable regime and how it could be affected by the other tipping elements in the climate system. Okay, thank you, Jung, and thank you, you all for listening.
Great talk. Unfortunately, CG cannot make it, so Ran will help us moderate the Q&A.
Yeah. So for now, we have 2 minutes. Actually, we only have 1 minute until the next talk. So if you have a quick question, feel free to ask. At the end of this of 2 talks, then we will have 10 minutes for more general questions. So anybody has a quick question to ask? Hi. Feel free to raise your hand or type the question in the chat. If not for now, we can move to the next talk and then ask questions at the end. All right, Pedro, feel free to share your screen.
Yeah, it looks like I can still not share my screen. Is there a way we...
I just made you a co-host. Please try again.
Yeah, sounds good. This is give me pandemic vibes. When we all were learning about how to do Zoom. Awesome. Okay. It's coming. Here we go. Thanks everyone for joining and for inviting me to present this work. I've been presenting some of these results since many AGUs ago, but this is the final distillation of our work. And it's a paper in review. Hopefully it's going to be out soon, like next year. So I want to acknowledge my collaborators and the NSF for funding our work. So there's many approaches to try to predict future changes in El Niño. And that's what we all want to do here. The most common approach is just running multiple models and hoping they all agree. And if they all agree, we will hope that there's some fundamental underlying mechanism that makes those predictions, and we will trust the models and we will be happy. And that approach has made a lot of progress understanding future climate change, but not for El Niño. Most models don't agree regarding future predictions, future changes in ENSO in response to in global warming. So we're trying a different approach. It's not that different. Other people have tried it, but it's for any prediction, we need 2 things, right? A common mechanism that drives what we are trying to predict in the future, and a period for validation. And for us, that period of validation is going to be the past, the geological past. We don't know which interval, so we're going to run a model for different climate intervals and see which one which of these intervals is useful to identify a common mechanism. But the other thing that we need is an observational target for validating this mechanism or our model. We do this a lot in predicting anything. It just happens that for El Niño, the historical record, it's not that it's too short, it's just ENSO is too variable on its own. So the historical record is not adequate for detecting externally forced changes in ENSO. There's a lot of research about that. So this target for model validation has to have a high signal to noise, a high force response relative to ENSO's intrinsic internally generated variability, which can be too large, as shown by also a lot of research since the pioneer work of Andrew Wittenberg. So our approach was to simulate key climate intervals over the past 21,000 years. This spans a wide range of climatic states. We perform them with the Community Earth System Model version 1. It's a model that has highly realistic ENSO dynamics, and I'll explain what I mean by this, but I think CSM 1 was probably the pinnacle of realistic simulation of ENSO dynamics. I've learned a lot about this model because I use it to predict La Niña and the asymmetric dynamics between El Niño and La Niña. This model is great for doing that, and I'll show you why that it's important to predicting changes in the whole ENSO phenomenon. We run the model sufficiently long, more than 500 years for each of these climatic states, to isolate the force changes, again, relative to ENSO's very large internally generated variability. And then we validated against multiple independent paleoclimate reconstructions for the intervals that we find common mechanisms. And just to anticipate the results, our interval is going to be the last glacial maximum, a case of a cold climate that we think is very useful to understand ENSO dynamics in the future. And I'll show you why. So we run the model every 3,000 years in a time slice approach, changing boundary conditions for these climatic intervals. So here I'm only showing the Holocene intervals all the way to 9,000 years before present. The 0 interval is pre-industrial conditions. And what we see in this plot, the y-axis shows the levels of ENSO variability measured by the standard deviation of the Niño 3.4 index. But here we're plotting them as a distribution. So I'll walk you through that. We subsample our runs that are very long into 30-year intervals, which is the typical length of paleoclimate records, just to show you the range of levels of ENSO variability measured by this metric, the standard deviation of the Niño 3.4 SST index, in these 30-year intervals over our simulations. And you can see that there's this box and whisker plot shows very wide distributions, and the medians, the centers of the box, show the actual level of variability. So these are not changes. You can see this is just the level of ENSO variability with its distribution. But you see that there's a trend simulated for the Holocene, but it might be undetectable, especially since we don't have a lot of corals for 9,000 years before present. Most of the corals are for the 6 and 3, where you can see that all these distributions overlap. So it would be difficult to detect a change, and this is consistent with the literature from corals that show that ENSO may be highly variable. And we can extend our view back in time to all these intervals every 3,000 years, and you can see that ENSO or El Niño is capable of large externally forced changes. The weakest levels of variability are in these intervals out of the deglaciation. Just one clarification, we did not run simulations with freshwater forcing. That was important during these intervals. So these results, have to be taken with a grain of salt, which is not including freshwater forcing, which will probably increase the variability. We know, and so typically increases variability in response of changes, weakening of the overturning circulation. But this is offering other intervals that we could use for validation, like the last glacial maximum, which shows weaker variability than the pre-industrial conditions, So we could validate these responses. A lot of overlap, and I'm going to address that. And the good thing, and those results from the LGM are consistent with previous work by Heather 4, and also by work by Xiang using this same version of the model. I'm just moving the screen just to show that we also run a simulation for the future at doubling CO2 concentrations, just to assess the mechanisms that will operate in the future. 2 times CO2 is about concentrations for 2050, halfway through this century. So the first thing we find is that the changes in variability in these climatic intervals are dominated by extreme El Niño. So this plot shows all the intervals, the distribution of the Niño 3.4 SST anomalies during the peak season for ENSO, November to January. So you can see that some intervals, the distribution is nearly Gaussian, like the colder intervals. Then you can see that ENSO is simulated in a skewed way. The Niño 3.4 index is skewed, so there's more variability, positively skewed, more variability in the warm tails because El Niño events are stronger. But if you zoom in, you'll see that the biggest changes in these distributions happen in these very high values of the Niño 3.4 SST index. So it's showing that extreme El Niño events are changing, their frequency is changing by a lot, particularly for the 2 times CO2 simulation with a huge increase in these extreme events. And then as we go into the colder climates, you can see the bluer curves here, those extreme events, El Niño events become less frequent. So let's look at this in a different way. We can find that across these climatic states, each dot is a climatic state. The percentage of extreme El Niño is correlated with the overall levels of ENSO variability. For doubling CO2, we have the strongest ENSO variability, and 1 in 2 events reach this extreme variability, which we define as events in which the peak Niño 3.4 SST index exceeds 2 degrees. And a very strong correlation with the colder climatic states, especially the ones in the deglaciation with almost no extreme El Niño and the lowest SST variability. So you'll think, well, these 2 quantities are related, but let me explain a bit more. If we think on an average simulated event, so this is how well CSM1 simulates the evolution of extreme El Niño events. The blue curve is a composite of all the events in our simulation, all the extreme events. And you can see that after the peak, El Niño is followed by La Niña conditions that last multiple years. And this is the research that I've done before, and that led me to approach this problem this way. The green curves are observed events. And you can see that this average composite event in the model evolves in the same way that observations. An extreme El Niño is followed by these persistent La Niña conditions. And then we go back to neutral until a new extreme El Niño event or a new El Niño event is triggered. But the overall variance of the ENSO phenomenon is controlled by how often these extreme El Niño events are triggered. And that's what we're seeing in the scatter plot to the left. The more extreme El Niño, the more variable the ENSO phenomenon is as a whole. So how do we validate our simulations? Well, the LGM has a lot of reconstructions of SST variability from single forum analysis. And we focus on surface and subsurface reconstructions. So this map is showing the surface, and the shading is the changes in the sea surface temperature variability simulated by our model for the LGM, applying reduction in CO2, changes in ice sheets, and changes in the orbital configuration and coastlines. And you can see that the blue colors indicate a decrease in variability. And this is total, and so total sea surface temperature variability. So it includes changes in seasonality and ENSO, among other ways the variability can change. But everything that is not steepled in the model is dominated by ENSO. So you can see that these 2 sites, these are the sites that Heather 4 used in her science paper, fall where the model the simulated changes are dominated by ENSO. So we can use this data to validate our model. And the color of the circles is already showing you the changes in sea surface temperature variability estimated from the proxies. This paper, Heather's paper, estimated SST directly from single forams using the magnesium calcium technique. And you can see, at least for site 849, which is the one that shows the largest changes, the distributions of the monthly sea surface temperature from the site, from the proxies, and from the model. So these are not the ranges of variability, how they conflict. So it's just the values that we have for monthly or for each individual forum in the proxy data to the left, and then in the model also sampled every month to the right. And you can see that both the proxies and the model show a decrease in variance. Although in the proxies it's a lot larger. And I'm going to show you how this is helping us attribute the changes at the LGM to the force changes that the model simulates. So this figure is a little bit dense. It's probably the hardest thing I'm going to show. And it's three different distributions. In yellow is the distribution of the percentage changes in variability from our model without any changes. So it's from the pre-industrial. And you can see this is essentially Andrew Wittenberg's results. There's a lot of internally generated levels of variability in the model and in ENSO. And then as we change different levels of variability using the simulations, we can look at how the distribution of these levels of variability changes. So blue is when we only allow the seasonal cycle to change. So essentially we combine anomalies from the pre-industrial and the LGM simulation, which has changed the seasonal cycle. And you can see that we're getting closer to the green value, which is the reduction in Heather's data, minus 40%. So it's a massive reduction that the proxies are showing at the LGM at that site in the Eastern Equatorial Pacific. And what we find is that the best way we explain the reduction, what we see in the proxies, is when we consider all of the changes in variability, including the reduction in ENSO variability that the model simulates, which is the red distribution. So we think that the paleoclimate data is best explained, at least this massive reduction is best explained by the reduction in ENSO variability simulated by the model. We also look at subsurface data, but I am anticipating that I'm going to run out of time, so I'm going to jump, and I'm going to try to explain the mechanism that we see in the simulations. So the first thing to think about is how the Bjerknes feedback works during extreme El Niño. Recall that the extreme El Niño are the energizers of the ENSO cycle in these simulations and in nature. So an extreme El Niño is triggered every time the trade winds relax, in general by a westerly wind burst. We like to think, sometimes we think it's thermocline anomalies that communicate that relaxation of the trade winds to the central and eastern Pacific, but it's actually zonal currents. When the zonal currents, the south equatorial current weakens, when the trade winds relax, it will allow the whirlpool to move to the central Pacific. And that's what you're seeing in this schematic that is based on observations. These arrows are those anomalies, surface currents that I estimated from ocean analysis. So you'll think, well, what's all that warming in the east? Is it not important? Well, it's really not that important because in the Eastern Pacific, the atmosphere and the climate is very cold. So even though we're warming a lot, the Kelvin waves triggered by these westerly wind bursts will warm it by a lot. They will not be able to influence the overlying atmosphere. So it's actually this warming at the edge of the whirlpool that kicks in the Bjerknes feedback, and the whirlpool expands westward. The Colton will warm up, but more forced by the Kelvin waves triggered by these changes in the winds. And once the central Pacific warms up, then the trade winds will further relax, and that's how we kick this version of the Bjerknes feedback. It's not how Bjerknes thought, and so we grow, but it's our contemporary view of the Bjerknes feedback for extreme El Niños, extreme El Niño events. So we estimated the growth rates for extreme El Niño from the model. So we used a technique that is asymmetric. So it only focuses on El Niño, not on La Niña, because they evolve in a different way. And then seasonally, which these are some of the advances that we did in this quantification. And you can see that this growth rate, which has units of 1 over time, is how fast the Niño 3.4 SST index growth at the onset of an El Niño event. It changes a lot in late summer, late boreal summer, across these climatic states. And again, we can correlate them with the amplitude of El Niño events. And we see that when this growth rate, which we define as the Viernes feedback strength, this growth rate during June to September is correlated with that peak amplitude of El Niño events. So climates that have a stronger Viernes feedback will trigger extreme El Niño events more frequently. So let's go back to the schematic and think all the processes that are involved. The response of zonal currents to trade winds depends on mechanical coupling. Zonal currents in different climates will be more responsive or less responsive to winds, depending on the position of the mixed layer. A thick mixed layer will be hard to move by the winds. A shallow mixed layer will be easy to move. There's 2 more couplings. The ocean thermal coupling, which is the one that most people think about. If you have a strong temperature gradient, once the currents weaken, the whirlpool will move faster to the east, and so forth for the opposite. And then wind SST couplings. Wind will have to respond to SST. So also, and this coupling is controlled by the whirlpool extent. So when we have a whirlpool in the mean climate that is expanding further east, is wider in longitude, then we have a bigger area in which SSTs can influence the wind. So all these 3 processes can influence the Viernes feedback and the growth rates that I showed you before. The nice thing of using a model is that we can compute all these couplings. So we did that from the simulations. And essentially this figure is my last figure and my second to last figure, but it shows how the Viernes feedback changes for the changes in each coupling mechanism in isolation. So the black curve is the total strength of the Viernes feedback, the one that I showed you before, that correlates very well with the overall levels of ENSO variability, in gray here with the distributions. And then purple, blue, and gold show what the Viernes feedback will look like when only one coupling changes in isolation. You can see that all the curves cross in the pre-industrial because that's the one that we use for reference. So as we go backwards in time, these couplings weaken. As we go forward in time, these couplings strengthen, with the exception of the thermal SST coupling, which has less of an influence. But the one that dominates it's the mechanical coupling, which was a bit of an unexpected result. So mixed layer is key, and I'm going to explain this again. So these glacial climates have a deeper mixed layer across the Pacific. A deeper mixed layer is harder to move. So every time the trade winds weaken, the zonal currents that will push the whirlpool to the east and kick the Viernes feedback will push it in a slower way. So the whirlpool will take longer to shift, will be slower to warm up in the Central Pacific, and it'll be harder to trigger an extreme El Niño. The opposite happens for global warming. The mechanical coupling increases the Viernes feedback because the mixed layer shoals. There's multiple reasons why the mixed layer shoals. And a shallower mixed layer is easier to move. Whenever the trade winds weaken, the zonal currents will respond more effectively and will more easily expand the whirlpool to the east, triggering the Viernes feedback. So it's ultimately what this is telling us. Oh, hold on, this is my last slide. So ultimately, extreme El Niño are controlled by the Walker circulation because the Walker circulation controls the depth of the mixed layer. And this figure is just showing you different features of the mean state that control these couplings. The mixed layer depth controlling mechanical coupling, the trade wind strength, which is the Walker circulation, and then the whirlpool edge, which is what controls the wind SST coupling. So together, these 2 couplings, the mixed layer depth and the whirlpool edge are what are controlling the Bjornes feedback across all these climatic states. And that is the common mechanism connecting past to future, and ultimately all related to the strength of the Walker circulation. So I'm gonna there's a common mechanism linking past to future. The level of ENSO variability are controlled by the frequency of extreme El Niño. The strength of the Bjornes feedback is controlled by mechanical coupling, but also by wind SST coupling under glacial and greenhouse warming. And ultimately, all this is tied to the strength of the Walker circulation, which is how global mean temperatures are linked to ENSO. We know that global warming weakens the Walker circulation, global cooling strengthens the Walker circulation. And that allows us to make this prediction that because we know that ENSO was weaker at the LGM from Paleodata, and this common mechanism links the LGM to the future, we should expect an increased frequency of extreme El Niño in a warming climate. I'll stop there. Thank you so much.
Thank you.
All right. If you have quick questions, clarification questions for Pedro, feel free to ask. You can either raise your hand or type your questions in chat. We'll start with clarification questions, and then we'll open up the floor for just questions to any of our speakers.
So
I have
no, just go ahead.
Sorry, who is asking?
Gabriel.
Sorry, can't see. Go ahead. You.
No, it's just a question. It's just a question for Pedro.
Yeah, go ahead.
Hey, Pedro. So you're saying that climatological states that tend to simulate an enhanced coupling in the equatorial Pacific would be associated with reduced ENSO variability, which is the case of the last glacial maximum. So you'd have a warmer pool that is pushed towards the west, and this would deepens the mixed layer depth, and then it would reduce the Bracken's feedback. And the opposite is shown for the future scenario. But how exactly do you think those changes are associated with the large scale warming? For example, you said that in cooler climates we have in strengthening work circulation, and in the future scenario we expect a reduced weakened worker circulation. But how exactly do you expect those mechanisms to be like more consistent across a wider change, across a wider climate states?
Yeah, that's a great question, Gabriel. So I think this mechanism, so the control of mixed layer depth and whirlpool extent on extreme El Niño probably works for any climatic state, since the overall levels of ENSO variability are controlled by extreme El Niño. So that's one result, and it would probably work for orbital forcing, for other forcings. But the ones that are important, I'm addressing your question about how global cooling and global warming influence ENSO. And I think it's a huge caveat of what I showed, is that it all hinges on global warming weakening the Walker circulation, which is by a mechanism proposed in a series of papers by Isaac Hell, Gabriel Pontes, and Brian Soden, which shows when moisture and precipitation don't increase at the same pace, and when the climate warms, then precipitation, which increases more slowly than moisture, requires convection to weaken, and that will weaken the ascending branch of the Walker circulation. The opposite happens for the LGM. In my 2012 paper, I talked about that mechanism in LGM simulations. So that's assuming, again, that models are representing these changes in mean state realistically, which is questionable. We have evidence for the LGM having a deeper mixed thermocline, which would be indicative of stronger trade winds. I think is one of the most, I mean, since I'm assuming everyone here is a paleo lover, you know, to me, that's one of the biggest questions our field is facing. What was the state of the Pacific during the LGM? I think we should be working on that. I'm sure a lot of us are working on that, but to me, it is an important question that it hasn't been answered, and we need more confidence on these model results. And then for the future, you know, we all know that in the last 40 years, the water circulation has been strengthening, which is the opposite to what models predicts. And that's another massive question that I think a lot more people are getting excited about now. And probably what we are at right now is a transient in which other processes like cooling in the Southern Ocean is, and ozone depletion is, and by its influence in the westerlies is affecting the tropics and driving this trend. Eventually, when the climate warms up, the water circulation would weaken. And again, this is a model result. I mean, probably our strongest evidence for this mechanism comes from the Pliocene. Just Uni has a bunch of papers showing that paleo data from the Pliocene, which is probably about 2 times CO2, cannot be explained without a weakening of the water circulation. So I think those are the gaps, I would say, or the holes, however you want to call them, in what I just showed. And the mechanism of the mean state controls and ENSO, I think, work because they are consistent with theory and the model does it. Then the influence of global mean temperature on the water circulation, I think, is the gap. And I think it's one of the most important questions we're all facing.
Great, thank you.
No problem.
I think there's a clarification question in the chat for Pedro. Where is the mixed layer from Jay Alder? So where is the mixed layer depths being sampled here in the figure? Are they sampled from Whirlpool?
Excellent. Yeah, that's a great question. I'm happy about them. You know, there's so many, the devil is in the details when you compute these growth rates and coupling strengths. And it has to be done on the Niño 3.4 index because it's where it will influence the coupling, the currents. So everything is done in the Niño 3.4 index. So it's close, you know, little east from the Whirlpool. We're using a fix of more clarifications on the technique. We're using a fixed box, so we're not moving this center of action of ENSO in these climate states. We probably should be moving it, but we didn't want to overcomplicate the analysis by moving the center of action. Although we probably should, but the changes are not that large that it really changes a lot. But you know, there's a lot more to do. My student Brandon Molina is looking into these details. So stay tuned.
Great. One more question for Pedro from Jack Hutchinson. So if more extreme El Nino become common and there are and these are associated with longer subsequent La Nina events or neutral state, could we expect for the average duration between El Nino to La Nina? I mean, between between El Ninos also increase. Sorry.
Yeah, I think I understand the question. Excellent question too, right? Everything is controlled by this very extreme El Nino, which trigger long-lived La Nina events. So we should expect more frequent, persistent La Nina conditions, which is also not good news. La Nina produces drought over many places throughout the world. My home country in Argentina, among many. And so more frequent extreme La Nina, more frequent long-lived La Nina means more frequent persistent drought. Brandon is working on this. He'll be presenting at AMS and you'll probably meet him soon. And we also think it affects the oscillatory dynamics of ENSO. So there's a lot more going on than just more frequent extreme El Nino. But that is the first order response in ENSO that leads to these overall increases and decreases in variance.
Right. So just clarify, Pedro. Do you mean just the extreme events, or do you actually talking about a shifting in the spectrum?
It's good. It's a good question. Yeah, there's changes in the spectrum. You know, we're working on that. So again, it's not really a shift. It's changes in the spectrum of ENSO with climate
maybe
change,
like broadening,
but more sharp, less sharp.
Right.
But the one thing I think is important to know, I mean, to me, the one thing that I learned by doing this is that it's not really, and this result is somewhat consistent with work that Wenju Chai has been presenting, is that it's not that the amplitude of El Niño events will increase, it's just the strongest El Niño events will become more frequent. It's really hard to increase the amplitude of the extremist El Niño, because that's controlled by the warm pole to cold zone temperature difference. So if you don't change the gradient, I mean, actually you have to enlarge the gradient to make stronger El Niño events, right? Like 1997 El Niño, it reached the temperature of the warm pole everywhere. And at that point, El Niño events stop growing. So what I like about this result is that it explains how a weakening of the temperature gradient can still lead to increased variance. It's not by making El Niño events stronger, it just makes them more frequent. And it leads to this counterintuitive result that a weaker temperature gradient east-west can produce more variability. But it produces it by making this extreme El Niño more frequent.
Got you. John, you have a question?
Yeah, it's already 4:03, and the people feel free to leave. And thank you for joining. I do have a quick question for Gabriel, if you have time and could stick for a few more minutes. So it's about a comparison with proxy data on the PAWS model simulation. So whether overall the models capture the mean state climate, or do we have any other reconstructions on the ENSO variability from the PAWS?
Yeah, so we do not have that much of proxy data for ENSO in the mid-Pliocene as we have available for the last interglacial and for the mid-Holocene. The few that we have, they indicate that especially in the mid-Pliocene, the ENSO variability was kind of similar to that of the late Holocene. But then during during the Pliocene, just for 5 minutes. Okay. So during the mid-Pliocene, from early to the late Pliocene, we had some changes in gateways that could have affected the tropical Pacific mean state, and we are not taking those into account when simulating the mid-Pliocene climate. So that should be one difference between what proxies say and what we are seeing in the mid-Pliocene simulations.
Okay, thank you. Thank you everyone for joining. Thank the two speakers for two excellent talks. Thank you very much.
Thank you, John.